Okay, welcome everybody to lecture 24 of CSE 548, the analysis of algorithms. Before we get started, are there any questions about logistics of the course, homeworks, any of the material we've covered so far? Okay. Okay. We're in again. We've been talking about NP-Completeness. Okay, and again, which is a sort of a complicated idea, except that the whole idea is really on this one slide. I've described the slide twice before. I want to go through it one more time just to make sure everybody sees what we're trying to do, okay? Because it's a somewhat slippery idea. If I give you an algorithm to solve some problem, okay, which works by translating that problem into another problem, calling a subroutine on that solves that other problem, okay, and returns the answer of that problem, okay, such an algorithm will be correct if the answer to the second problem on the translated instance is the same as the original problem on the original instance. If we can do the translation in such a way that the answers are preserved, this is going to be a correct algorithm, okay? And the whole idea is sort of how do we do the translation? But what's the implication? If we can translate our problem into some other problem, if we have a fast way to solve that other problem, that gives us a fast way to solve this problem. Okay? Bandersnatch can be solved quickly if mobility can be solved quickly, and we can do the translation quickly. But if we know that Bandersnatch is doomed to take a lot of time, we have a lower bound proof or some kind of an argument that Bandersnatch is definitely hard. If we can solve it quickly, if mobility could be solved quickly, the important thing that means that mobility cannot be solved quickly. Okay? Because a quick way to solve this would imply a quick way to solve that. Okay? And there is no quick way to solve that. Therefore, there is no quick way to do that. That's how we're proving hardness. Okay? And if you're confused about the directions of reductions or what we're doing, always go back to the slide and rethink it. Okay? Any questions about what we're doing here? Okay? How many people think they understand what this slide is doing? Which way is correct? Okay? How many people feel they're still confused about that? Okay? The basic idea, again, if we have a way to translate our problem into something else, a fast way to solve this problem will give us a fast way to solve this, okay? Because we just simply do the translation and do the solution. What we're saying instead is if there is no fast way to do this, and we provide some other way, which would be fast if something happens, okay? That means that other thing that can't be true, okay? It can't happen, okay? And so the hardness of the second problem results from the first one, okay? If you don't get that yet, come back and we'll talk about it. Okay, it's important, though, to see what the basic idea is. Okay? Any questions? The other subtlety, just before we get started, that's another point of confusion. First of all, you have to note the direction of the reduction. Okay? We're trying to prove hardness. What does that mean? We want to translate, we have a hard problem that we know is hard, and a problem we don't know how hard it is. Which do we translate into what? Okay? If we want to prove something's hard, do we translate the hard problem into the easy problem, okay, or the unknown problem, or do we translate the unknown problem into the hard problem? Okay? How many people vote that we translate the hard problem into the unknown problem? Okay? That's how we prove it's hard. We translate the hard problem into the unknown problem. Okay? If you translate the unknown problem into a hard problem, all you've done is give a slow way to do your unknown problem. Means nothing. Okay? That's important to see. Question? Well, does it mean that you can translate one way to the other way? Not, if you translate one way, does that mean that you can translate the other way? The answer is not necessarily. If you think about it, it should be fairly, if you have one problem that's very slow and is very hard, and one problem that's very easy. It shouldn't be, it might not be, it seems quite reasonable to me that you could solve a very easy problem using a very slow problem. Okay, so for example, I'm pretty sure there's a way you could solve shortest path by using the traveling salesman problem. Okay, it wouldn't surprise me if you could come up with a way to translate shortest path into traveling salesman. But what would that give you? That would give you simply a slow way to solve something. There's a faster way to do it. If you could find a way to solve traveling salesman using shortest path, then you found the fast way to solve traveling salesman, and then we can talk. Okay, but you're not going to do that. So the reductions don't necessarily go both ways if one problem is easy and one problem is hard. They will go both ways usually if both problems are hard. Okay? Any questions? Okay? So the other thing to note is that when we do our translation, we're translating our hard problem into our unknown problem. We've got to translate all possible instances of the hard problem into the unknown problem. Okay? So what does this mean? If you think about it, when we talked originally about satisfiability, if we were trying to prove something with satisfiability as our hard problem, we've got to translate all possible variations of satisfiability with 3-sat, 4-sat, 5-sat, 6-sat into instances of our other problem. Okay? Instead, what we're doing, okay, with 3-sat is a special case of satisfiability. It has less instances in it. There are things that are satisfiability problems that are not 3 satisfiability problems. Because we proved that 3-sat was hard, though, it suffices to translate any 3-sat instance into our problem. Okay? The important thing to see is that once we have a hard problem, we have to translate all possible instances of that into something else. Okay? And so, for our purposes, it's best to work with as restricted a hard problem as possible, which is why 3-sat came in. Okay, any questions? Okay? So when you get confused, think about the direction of the reduction. Okay, and I'm sure you'll get confused at least once. To me, it always seems backwards. Okay? That's why you got to think it out each time you try to do it. Any questions? Okay, so far, the only reduction that I've shown you was from satisfiability to 3 satisfiability. Okay? And you may say, well, I don't care about satisfiability. That's not a very interesting problem. I've never had to solve anything. People don't pay money to solve SAT problems or something like that. Let's now translate to a completely different kind of a problem, or seemingly completely different kind of problem. Okay? A problem that comes up in operations research, okay, and combinatorial optimization all the time. The linear programming problem. What is the linear programming problem? Or the integer programming problem, excuse me. You've got a set of integer variables, okay, a set of inequalities over those variables, some kind of a function you seek to maximize, and some kind of a integer b. What's the question? Is there a way to assign integer values to those variables such that all the inequalities are true, okay, and that optimization function value is greater than our bound? So what is the integer programming problem? Okay, basically it says that you've got a set of constraints, okay, on a bunch of integer variables. For example, v1 has to be greater than 1, greater or equal, v2 has to be greater than or equal to 2, v1 plus v2 has to be less than or equal to 3. You've got some kind of an objective that you're trying to maximize. Okay? Here's a function that says 2 times v2. And the question now is to try to find variables assignments. The optimization problem is how to find variable assignments to those integers to assign to those variables such that all the constraints are satisfied and you get as big a payoff as possible. Why is integer programming an important problem? Well, let's say that you're a company and you want to figure out how to invest money. Okay? You may have certain constraints as to how much you can spend on money. Let's say like you're only allowed to spend 20% of your assets, okay, in each of a bunch of different sectors, okay? Let's say you have to spend a certain amount of your money, in the United States and a certain amount of your money in another country. You can model these kind of constraints, okay, as inequalities, okay? The total amount that I have to spend in the United States plus the total amount that I have to spend in England has to be less than $3 million, okay? And so on. And what's your objective? Your objective is to find a way to spend your money on different things to maximize your profit. So a lot of different optimization problems come out as integer programs. Okay? The airlines are constantly solving integer programs trying to solve integer programs to try to figure out how to make the rate schedule complicated enough, okay, for them to make as much money as possible. That's how you get all these constraints about, well, if you stop over 7 days early, and how come it might cost more to fly directly to someplace than it is through 4 or 5 cities. The reason is because they're coming up with very, very complicated objective functions, and they're trying to maximize their profit. And underlying all that scheme is basically an integer program that they want to solve. Okay? So this is an important problem. This is something that does come up all the time. And if you're one of the students from applied math, you eat and breathe integer and linear programs. Okay? So what's the example? Here we've got a case where we've got, again, these 3 constraints. My claim is that if you want to satisfy these constraints, v1 is greater than 1, v2 is greater than 0, v1 plus v2 is less than 3, and maximize 2 times v. What would be the assignment here? If you want 2v2 to maximize, you want v2 to be as big as possible. The sum has to be less than 3. v1 is constrained to be at least 1. If we make v1 as small as possible, which would be 1 to satisfy that, we can make v2 as big as 2. 2 times 2 is 4. 4 is bigger than our bound of 3, so yes, this would satisfy it. Okay? So this is a solution to this integer program. Or are there any questions about the problem? Okay? Looking at another one, suppose we have a program, v1 is greater than 1, v2 is greater than 0. Again, the sum of these things is less than 3. Our function's the same. Everything's the same except for our bound. Can we achieve a value of 5 using this? The answer is no, because the largest we could possibly make v2 by our previous analysis was 2. 2 times 2 is 4. No way we get up to 5. Okay? So what is the integer programming problem? Given the constraints, given the optimization function, okay, is there a way to assign integers, okay, to this thing that satisfies all the constraints while satisfying the optimization function? Okay? Any questions? Or do people feel they understand the problem? How many people feel they know what I mean by the problem? How many people are confused? Okay? Any questions about when people are confused? Anything in particular? The goal here is this. The problem is you're given some constraints on these variables. Okay? You're insisting that v1 and v2 are less than, or the sum of them is less than 3. So you could choose any values of these so long as they satisfy this and that. Okay? Your goal is to try to maximize this function subject to its constraints. If you didn't have any constraints, what's the maximum of f of v you could get? How would you maximize this value? You could realize if you had no constraints, you could make this value infinitely large by simply making v2 as large as you want. Okay? But in the real world, there's often constraints. Okay? So the constraints are modeled by these linear inequalities. Okay? And your goal is to try to satisfy all the linear integer inequalities while maximizing that function. Okay? That's the problem. Okay? So what do we want to do? We want to prove this problem is hard. Okay? How do we prove it's hard? What is the technique to prove a problem is hard? We have to take some known hard problem and reduce it to the problem we're curious about. Integer programming is the problem we want to solve. Okay? What should we use as our known hard problem? Okay? So far, you don't know too many hard problems to choose from. What would you choose? You have a choice of satisfiability or 3 satisfiability. Okay? Turns out, for this case, it really doesn't matter. But normally, you would say, I want to use the simpler of the problem, so I would normally use 3 set. Would make it easier. But it doesn't really matter for this one. Yeah?
How can you tell in general which problem to choose?
Okay.
For example, if you know TSP.
It's a good strategy question. In order to prove a problem is hard, you have to start from some problem. Which problem do you start from? In theory, any problem is equally as good as any other problem. Okay? In practice, it can be vastly easier if you start from the right problem. Okay? Later on, I'll talk about strategies for picking the right problem. Okay? But my basic idea is you look for, typically you only know a small number of hard problems. Okay? You'll know satisfiability is hard. Okay? You'll know later on, I'll show you vertex cover is hard. Later on, you'll know integer partition is hard. There's a set of about 5 or 6 problems that I use to start from. Okay? I prove things NP-complete, almost for a living. Okay? And there's a set of like 4 or 5 problems that I always start from. Their satisfiability, or specifically 3 set, their Hamiltonian cycle, their vertex cover, okay? And there's integer partition. And those are usually the problems that I start from. Okay? And almost always one of them will suffice. Picking the right one means to try to identify which of these problems is most like the one that you want to prove hard. Okay? And part of that is sort of a taste that you develop. Okay? You look at the problems and see which closest. I'll try some examples later on, and we'll try to go through that. Okay? But you have to use some judgment here. Okay, any questions? Okay, so how do we prove integer programming is hard? Well, the only thing you really know so far is hard is satisfiability. How is satisfiability like the integer programming problem? If you think about it, there's some similarities between them. Okay? Satisfiability problem has what? It has variables and it has clauses. What does integer programming have? Variables, a function, and more than that, constraints. Okay? What is the principle here? Every one of these constraints has to be satisfied. Okay, correct? In order to, you have to find a set of variables that satisfies all these constraints. Okay? That should sound a lot like the satisfiability problem. What is the satisfiability problem? You've got some Boolean variables, 0, 1, and you want to figure a set of clauses. You want to find the set of assignments that satisfies each clause. Both problems seem in some sense quite similar if you think about them that way. So how can we translate from satisfiability to an integer programming problem? Okay? My idea is going to be, I'm going to create an integer programming problem that's going to have twice as many variables. There's lots of ways you could do this translation. This is probably the one I think is simplest. We take every variable in the satisfiability instance, okay, vi, and what we're going to do is create 2 different, this is a Boolean variable. Remember, this is equal to true or false in sat. What I'm going to now do instead is create 2 variables associated with this, vi and vi bar, both of which are going to be integer variables that are going to correspond to this variable, the logic variable. Okay? And I'm going to use constraints to make sure the variables behave in the right way. So what am I going to do? If this variable is going to be either true or false, I'm going to try to come up with integers that correspond to true and false. What are good integers to correspond to true and false? 0, 1. Any C programmer knows that. Okay? So why don't I first add some constraints for each variable, saying vi is between 0 and 1, and vi bar is between 0 and 1. What does that mean? Since these are integer variables, what are the possible values, integer values, vi can take on? It can take on the value 0. It can take on the value 1. Can it take on the value of 1/2? No. Why not? Because these are integers. The problem said that they are looking for an integer solution. Okay? The only integers between 0 and 1 are 0 and 1. So adding this constraint and this constraint guarantees that all the variables that I have will have 0 or 1 solutions in anything that satisfies all the inequalities. Okay? How many people believe that? How many people are confused at this point? Okay, good. Now, what is this going to mean? This is going to be v sub 1. This is going to mean corresponding to the real value of v sub I. This is the complement value of v sub I. What do we want to be true if v sub I is equal to 1? What do we want v sub I bar to be equal to? 0. If v sub I is equal to 0, what do we want v sub I bar to be? 1. So we need some way to tie these two variables together, correct? Because we want to make sure they're consistently true or false. We run into trouble if we say v sub I is true and v sub I bar is also true. Okay, got to prevent that. So we can prevent that by adding another linear constraint. Suppose I insist that v sub I plus v sub I bar, okay, is greater than or equal to 1 and less than or equal to 1. What does that mean v sub I plus v sub I bar is equal to? It's equal to 1. So you've got two things that are adding up to exactly 1, both of which are either 0 or 1. So is it possible for both vi and vi bar to both be 0? No. Is it possible for them both to be 1? No, because then that'll be 2. By adding this constraint for each one of the Boolean variables I transformed, I've now got a constraint that none of my two variables are chained together. They do not have the freedom to be arbitrarily. They only have the value to be complements of each other. Okay? How many people believe that? How many people are skeptical? Okay? Good. Now, the other thing that I need to do for satisfiability, now I've got my variables behaving properly. Each one of them is true or false. Okay, and the complement of true is false, so that's a good thing. But I now have to make sure every single clause is satisfied. What was a clause, remember? A clause was a set of Boolean variables and their complements. And I wanted to make sure that at least one of them was true. Correct? That's what satisfiability was doing. So what does one of them being true mean? It means that at least one of these variables has to be true, or in our notation numerically, 1. So what if I take this clause and rewrite it vi plus vi bar, v2 bar plus v2 bar, add up the integer variables corresponding to each of the Boolean variables, complemented or not, in the original clause, and make that greater than or equal to 1. What does this mean? If this inequality is true, what does that mean? At least one of these integer variables has to take the value of 1. Can more than one of them take 1 and this be satisfied? Sure, there's nothing wrong with satisfying lots of variables in a clause. But is it possible for them all to be false? No. My claim is these constraints are exactly the constraints that you get in satisfiability. Okay? You can translate any satisfiability instance into exactly these constraints. Okay? And they constrain the integer variables the way the Boolean variables were constrained in the other problem. What's the other thing we need in our integer programming problem? a maximization function. But if you think about it, we don't really have to make that very complicated. We've already translated everything there is to translate in satisfiability. So it turns out, actually, the maximization problem is really unimportant. Let's just say we want a variable v at 1, so where v1 is greater than 0. Okay, so our bound is going to be 0. So our optimization goal is to say, is there a way to satisfy all the constraints such that variables v1 is greater than or equal to 0? Certainly there's a way to solve this optimization thing if you can satisfy all the constraints. And if you can't satisfy all the constraints, satisfy this, because that's the first thing. You have to satisfy the constraints. So what is it that we've done? Okay. We've done a translation where we need to show that every satisfiability, we have our SAT problem here. We translated it to integer programming. Okay? Every clause that we had here became every variable became a series of integer constraints. What's the point? If we have a satisfiability solution to this SAT problem, my claim is that gives us a solution to the integer programming problem. Why is that? If you give me a SAT solution, you're now telling me that there is you've now found how to assign true, false to all the variables such that every clause is taken. If so, give me that answer. Whenever there is a true literal, I'm going to set that to be 1 in my integer program. Whenever there was a false literal, I set it to be 0. I know all my variable constraints are taken. They're satisfied. I know all my sum constraints corresponding to clauses have at least one thing equal to 1 in it. So that's taken care of. My claim is it should be obvious that if you give me a satisfiability solution to the SAT problem, that defines a set of integer values that satisfies the integer program. How many people believe that? Okay, how many people don't believe that? Okay, more people. Yes, question.
When you reduce SAT to IP, the maximization function,
right.
Sort of, in a sense, trivialized it.
I trivialized the maximization function. That's exactly what I did here.
So, how then does the SAT solution give a solution to the IP problem? Because the IP problem
how does the SAT problem solution give a value to the IP? This particular integer program says, I will take whatever solution you give me will satisfy my maximization constraint, so long as you satisfy all my integer inequalities. Okay? It's sort of like something that says, I don't care how much money I make, so long as you don't violate any laws. That's really what the case of this inequality is. Okay, it's a special case of the integer program. Okay? General integer programs may have very complicated maximization functions. But I'm saying you don't need those complicated maximization functions in order to prove the problem is hard. Even a trivial maximization problem is going to be enough to show that the problem is hard. Remember what we're doing. We're translating SAT into the integer program. We have to translate all SATs into integer programs. But the features of integer programs. Okay, I mean, think about it. We're trying to show that this is at least as hard as that. If you're saying, hey, look, I can solve SATs using integer programs without fancy max functions. Okay? Adding the possibility of a fancy max problems might make it even harder. But it certainly can't make it softer, because without that capability, I'm already able to solve all SAT problems. So this becomes at least as hard as that. Question? Okay? Right. Note what this is. All input instances have to be mapped into something, but we don't have to necessarily get every single integer program that's possible under the sun. Okay? Think about any kind of a translator. Your goal is to translate everything that could come in on this side into something on this side. Okay? If you want to write a program that translates Russian into English, it's important that you be able to translate any Russian sentence into an English sentence. It doesn't necessarily mean that you can create any English sentence that's possible. Okay? Because maybe there's no corresponding Russian or something like that. Okay? So you have to translate all possibilities here into some possibilities here. That's enough to prove the hardness, because we have to show if we can do this guy has to be as hard as that. And this guy's hard. Okay? So any questions about the direction? Question? Okay? What's the point here? What was the integer programming problem? Let's go back to the definition of the problem. We've got a set of variables, we've got a set of constraints, and we've got a maximization function. Okay? We have to, what's the problem? We have to satisfy all the constraints, and we seek to maximize the maximization thing, given that we've satisfied everything. That is integer programming. Okay? What is true about our solution? We've translated satisfiability such that all the Boolean variables correspond to integer variables and they behave properly. We've translated each clause such that if the clause was satisfied, that meant that there was a true literal. We have an integer inequality such that it demands that there has to be at least one guy that's true in each one. Together, that captures all of what is in satisfiability. We now have the freedom to pick any maximization function we want. We are doing the translation. Okay? If we say, give a maximization problem, which is trivially solvable, okay? Saying, look, we know v sub I is either equal to 0 or 1 by our constraints. We say maximize v sub 1 or and we'll be happy so long as you can get a. If you can satisfy all the constraints, you have to be able to satisfy all the constraints such that v sub 1 is greater than 0, greater than or equal to 0. Okay? So basically, this is a trivial maximization problem. Okay? So the maximization function is not what's making it hard. The hard part of the integer programming, it turns out, is not maximizing something, but just satisfying the constraint. That's really what we're saying here. Okay? Questions? Okay? So does everybody, how many people feel they see the mechanics by which we translate SAT into integer programming? Okay? How many people are confused by that and want to see it again? Okay? Nobody. Okay? The important thing to see here is we've translated every single SAT problem into an integer program. Okay? And have captured the hardness of that. Yeah? We need to translate every single instance of our hard problem into some instances of what we're trying to do. Okay? We don't have to translate it into all possible instances. Now think about why that is. Make sure you understand why that is. Okay? We're trying to say Bobilli problem is hard. Okay? Why is the Bobilli problem hard? Is it because every single instance of Bobilli is hard? No. Okay? We're saying that the worst case of Bobilli is hard. Why is that? Because if you could always solve Bobilli, I've given you a way to always solve Bandersnatch fast. Bandersnatch is hard. Okay? Bobilli can do everything Bandersnatch can, maybe some more. So Bobilli has to be at least as hard as Bandersnatch. Okay? And Bandersnatch is hard. So that's why it's that way. Okay? How many people see that logic? Okay? How many people are still confused about it? Okay, or have any questions? Okay? So what's the point? What are the things to notice in doing this translation? First thing to note is that in the course of translating the problem, we did not solve the problem. Okay, this is the satisfiability problem in the course of doing our reduction. Did we worry about what the answer to the satisfiability problem was when we did our reduction? No. All we did was translate the raw input. Okay? So we're really just reformatting the input, not actually solving anything. This isn't a people get confused with. Okay? It's hard to say, well, if I know what the answer to SAT is, then I can do the translation. But you don't know what the answer to SAT is. It's a hard problem. You want to reformat the input. Okay? As I said before, the set of possible integer programming instances which can be resulting from this translation is a small subset of all possible ones. Okay? But since some of these are hard, the problem in general has to be hard because we're talking about worst case. Okay? Any questions about that? That's an important thing to see strategically. Okay? The other thing is that once you see the translation, again, realize that you're learning something about integer programming. Not just that it's hard, but you're learning why it is hard. Okay? Maximization has nothing to do. Function has nothing to do with why it's hard. Having big integers in your variables has nothing to do with it being hard, because limiting them to 0 and 1 is enough to prove hardness. So you learn a lot about where really the hardness is in integer programming, not just that this big monolithic problem is hard. Okay? And so a study of our reduction tells us what the problem is. Okay? Any questions there? The final question, which is a subtlety which I don't really want to go too much into. Normally we say that any problem we reduce, okay, we say that that problem is an NP. Okay? What did we say NP was last class? NP was the set of problems that you could verify the solution. If somebody told you the solution, you could convince them that you were right, that they were right in polynomial time. It turns out it's not obvious that integer programming can be verified in polynomial time. Why is it? Somebody could give you an integer program, and maybe the only solution to that integer program involve numbers so humongously big that you couldn't write down the numbers and add them up in polynomial time. Okay? Remember, it's time polynomial the size of the problem. So if you catch the subtleties of what something is in an NP, integer programming is one which is not obvious. Okay? But it turns out that with some more arguing, you can in fact show that the variables numbers don't get so large. Okay? So again, if you're confused about NP, ignore this. Okay? But if you understand what I'm saying, this is an example of a problem which it's actually harder to prove that it's NP than to prove that it's hard. Okay? Any questions? Okay, very good. So, what was the problem of the day? The problem of the day asked, okay, again, I pulled a switch at the last minute as to what the problem of the day was, last class, said basically, given an integer n by m matrix and a vector, okay, an m-element vector, the 0-1 integer programming problem asks whether there is an integer vector, okay, with values in 0, 1, such that matrix A times x is less than or equal to b. And they ask you to prove it that problem is hard. If you think about it, the problem I just proved was called integer programming. Okay? And this is asking for integer programming. So likely it shouldn't be very difficult to convert that problem into this problem. Okay? And in fact, it's not. this linear algebra notation they're saying, remember, is you've got some matrix. You want to multiply that by some vector x such that everything is less than or equal to some vector b. So what is that going to be? The first value here is going to be saying we're going to take this times this, this times that, this times that, this times that. These are the variables. These are the constraints. Okay? When you think about the linear algebra formulation for the problem. Really what this is saying is that A11 times V1 plus A12 times V2 plus A13 times V3 is less than B1. So this problem is really, every row here corresponds to a constraint once you parse the linear algebra notation. Okay? And the only other difference between this problem and the one that I talked about is that here all the inequalities are restricted to be less than inequalities. If you have some constraint, x1 is greater than or equal to 5, how can you make this a less than inequality? Okay? Multiply both sides by a negative number. And now it's a less than inequality. So once you understand the other thing that I was doing, and you understand the linear algebra notation, there's no difference between this and that. Okay? And you can think about that if you wish. Okay? I find the other notation is easier to think about. Okay? But if you don't, think about that. Any questions about the integer programming hardness proof? Okay? Again, think about it. The actual structure of that, once you understand what integer programming is, that's actually a pretty straightforward reduction. And you really should believe that one and understand it, okay, before you get into some more complicated reductions, like we're going to talk about now. Okay? Any questions? Okay? Let's look at a second reduction. Okay? Integer programming was a number problem. Okay? Satisfiability was a logic problem. We just showed that a number problem was hard. Most of the semester we talked about graph algorithms. Let's now prove that a graph algorithm problem is hard. Okay? What is a graph algorithm problem? Here's a specific problem called vertex cover. Okay? Which comes up a lot in certain scheduling problems. Variations of this tend to come in scheduling problems and pattern recognition problems. This is a good problem to know about. Okay? What is the input to vertex cover? The input is a graph and an integer k, which is less than the number of vertices. Okay? The question is there a subset of at most k vertices such that every edge touches at least one of the vertices in our set? Okay? So look at this pretty graph. Okay? My claim is look at those circular vertices. I claim that every single edge in the graph touches at least one of the circular vertices. Right? Look at this edge. It's got that guy. This edge has that guy. This edge, and this edge. Well, but this edge has that guy. This edge has that guy. This edge has that guy. This edge is blessed by touching two of them. Okay? One is enough, but this guy's got a double coverage. This guy's got double coverage. This edge touches this. This edge touches that. Every single edge in this graph, I claim, borders on one vertex of the circular types. My claim is that means that the circular vertices form a cover. Okay? First thing is to make sure you understand the definition of the problem. Okay? And one source of confusion may be that there's lots of problems coming at you now. Okay? But so what is the vertex cover problem? We're seeking to find a subset of vertices such that every edge borders on, touches one of these vertices. Okay? Why might such a thing come up? Let's just try to think of something. Okay? If you think about it, let's say that you want to you may think of the edges as, let's say, people. One way maybe to think about it is edges being some kind of people. Okay? And the vertices may correspond to being groups. And you want to know how many groups do you have to send email to in order to guarantee that every person is reached by sending mail to some group. Okay? That's really what's sort of an example of what's happening here. Yeah. Okay, so let's think about it, first of all. First of all, do the black vertices, these vertices here, do they form a vertex cover? Okay. How many people think these black vertices form a vertex cover? Okay. How many people think they don't form a vertex cover? Okay. Good. Why not? What edge is not being touched by one of these little black vertices? The ones that are touched by two in the cover, in the other cover. Okay? So the point is, not every subset is a cover. If every subset was a cover, the object of testing if a subset was a cover would be trivial. Okay? Now, can everybody give me an algorithm to find a vertex cover? A very simple algorithm to find a vertex cover of a graph. Yeah. Okay, one possibility with test, if we're looking for a cover, okay, what would be the simplest algorithm one can come up to find a vertex cover of a graph? Just return every single vertex. We know every edge touches every edge touches two vertices. If I return all the vertices of the graph, then I'm guaranteed that, in fact, I have a vertex cover. But that's not much of a feat. The hard part, okay, if we think about it, is finding a small cover, a small set of vertices that take care of all the edges. Okay? So that's really where this bound K comes in. This says, given a graph, find me a vertex cover whose size is less than my bound. Okay? And so if you think about it, the hard thing is finding the small cover, not finding a large cover. Okay? Any questions about vertex covers? Okay, question? It's basically an optimization problem, but almost all the problems we're going to deal with in here are optimization problems. Okay, well, that's not completely true. Okay, it's an optimization problem, but we're making it a decision problem by adding this integer k. Conceptually, you want to find the smallest sized vertex cover. The question here says, is there a vertex cover of size at most k? So I ask you, is there a vertex cover of size 17? That becomes a yes-no question, a decision problem. Okay? But it gets to the heart of what makes this an optimization problem. Okay? Questions? Okay? So what is our idea? We want to prove that vertex cover is NP hard. Okay, a hard problem. How do we prove that the problem is hard? What's the general strategy we need? We need to find a hard problem and do what with that hard problem? We need to translate that hard problem into vertex cover. Does it help to translate vertex cover to that hard problem? No, because all you would have done is give a slow way to solve vertex cover. We need to try to translate vertex cover into something else. What would be a good choice for a problem to translate? What are the hard problems we know? We know satisfiability. We know 3 satisfiability. We know integer programming. These are all problems that maybe look a lot alike so far. Which is the simplest of those 3 problems? Simplest in being most restricted. Okay? 3-sat. 3-sat is clearly more restricted than satisfiability. And it's more restrictive than integer programming. But now if we want to translate integer programming, we've got to worry about all maximization functions. Okay? Where we didn't have to worry about that before, because we had to translate all instances. So my choice from what we know so far would be to start from 3-sat. Okay? And now we have to translate every instance of 3-sat into something else. Into what? What do we have to translate 3-sat into? Into a graph and an integer. Because we have to reformat the input of 3-sat into an input of this. Okay? So what's the point? What is the input of satisfiability? What do we have to? What does the input to satisfy 3-sat look like? What do we have? We have clauses of 3 variables. Ci equals some clause of 3 variables. And what else do we have? Boolean variables. Vi, is true or false. So we now have to translate this into a graph. Okay? How do we do it? It requires cleverness. Okay? But this is kind of neat. First thing we're going to need to do is we're going to show that we can take a 3-sat instance with n variables and c clauses. We're going to construct a graph with 2n plus 3c vertices. Okay? Where do these numbers come from? They come from the construction. I'll show you the construction in a minute. Okay? What is the idea? We first need to translate each variable. Yeah, question? Oh, okay. How do I know this number beforehand? Well, I don't know it. I know it because I know the reduction that I'm using. In general, you don't know this before you come up with your proof. You know you want to do a translation, and you don't want to construct a graph without too many vertices. Okay? But this comes as a result of analyzing the construction I'll show you next. Okay? So this is not something you know at this point. Okay? But what do you know? You want to try to find a way to translate each variable into a graph thing. But what is a graph thing? A graph thing is vertices and edges. What if, for every variable, I were to create 2 vertices? Each variable is a Boolean variable, correct, from SAT? So each vertex can take on the value true or false. Okay, so one's going to be VI, one's going to be VI complement. V2, V2 complement. V3, V3 complement. If I have n vertices, how many pairs of n variables in my SAT problem? How many vertices am I creating here total? 2n vertices. How many edges have I just added? N. If I want to find a vertex cover of the graph so far, what was a vertex cover? A subset of vertices such that every edge is bordered on one. What would any vertex cover of just these edges look like? It would have to be one of either of these, one of either of these, plus one of either of these, plus one of either of these, plus one of either of those, right? Now, as I add more edges to my graph, could that ever change this? If I need to cover this edge, if I add more edges to my graph, am I ever going to be able to pick any other vertex other than this or this to cover that edge? No, because this edge touches on 2 vertices, right? If I want a vertex cover for my whole graph, which is going to include more stuff, if I'm going to cover all the edges, I'm going to have to pick one of these 2. Because that's the only way I can get this edge. I can add more stuff coming off of here. But that isn't going to help me cover this edge, is it? So what I claim I've proven is, in order to cover just these edges, I would need to pick one of these, and one of these, and one of those, and one of those. Okay? How many people believe me on that? How many people don't believe me? Okay? Any questions at this point? Okay? Question. Okay? Conceivably, if I wanted to just cover these edges, I don't actually need to double cover just to pick up these edges. You might say there might be a situation where, let's say I have a graph that looks like this. You're saying, why don't I just pick this one, and then I'll cover all those edges? So I'm going to have to add more to my graph to make sure I can't do that. Okay? So here I've translated my variables. Question? Why do I want to prove this? Yes, this factor of n? It's because you'll see why later on. What are we trying to do? We're trying to figure out a way to translate our SAT problem into a graph. Okay, a specific graph whose vertex cover properties are going to mirror our SAT properties, right? So by doing this translation, I've got a point where I'm going to have to pick at least one of these. If you think about it, here you start seeing where the SAT problem might start to emerge. Because the SAT problem is going to mean picking one of these to be true, and one of those to be true. So when I do this is sort of where the ideas are going to be emerging from. Okay? I'm going to use this to show that somehow this is going to correspond to true and false. This corresponds to my Boolean variables. Okay? Any further questions? What else do I have to translate in my SAT problem? Okay, I've translated my variables. What else do I have to translate? What do I have to translate? My clauses. What are my clauses? Each clause contains 3 literals in it. Right? Why is that? Because it's 3 SAT. What I'm now going to do is, for each clause, create 3 new vertices. One which represents each literal in each clause. Okay? So for example, let's go down to this picture. Here I've got a triangle. This is V1, V4 prime, V3 prime. My claim is this corresponds to that clause. Okay? You give me a 3 SAT clause. I am going to construct a triangle, okay, which contains 3 vertices and 3 edges corresponding exactly to that clause. So what clause does this triangle correspond to? V1 prime, V2, V4 prime. Okay? What do I know? Okay, so what am I doing? I'm now translating each clause into a triangle. I translated each variable into 2 vertices connected by an edge. What is true about this triangle? If I just give you a triangle, how many vertices do I need to pick up in a vertex cover to cover all the edges of that triangle? 2. Which 2? Any 2. Okay? I could cover it with this one and this one. And all edges now are touching that. Could I cover it with 1 vertex? No, because this guy's left out in the cold. Okay? I could cover it with 3 of them, but that's more than I actually need. So what am I saying here? I'm saying that if you cover, I'm going to build a graph which is going to contain a triangle for each clause, a pair of vertices for each variable, and some extra edges. Okay, I'll tell you how to build the extra edges in a second. But what's the point about the vertex cover of this thing? In any vertex cover of this graph, I'm going to have to pick at least one of each of these, correct? And I'm going to have to pick at least 2 of these out of each of those, correct? So what do I know about any vertex cover of any graph that contains these plus extra edges? My claim is it's got to be at least as big as n plus 2c. Why? Because I've created a triangle for each clause, to cover this triangle, I need at least 2 vertices. Correct? I've created C of those. So that says that I need at least 2C vertices in my cover to cover all the triangles. Okay? I've created n of these units. I said I need to pick at least one of these, one of these, one of these. At least n vertices to cover just those edges. So my claim is any vertex cover of this graph has to have at least n plus 2c vertices in it. How many people believe that? How many people don't believe it? Okay? Question?
If you choose, for example, if you choose vertex 1, you can just choose vertex 4 to cover the below triangle.
No, you're saying if I just pick vertex 1 and vertex 4, you're saying I can completely cover this triangle? No, you didn't cover. But what about this edge? What about this edge? How are you going to cover that edge? Can't do it. You need to pick 2 of these. Okay, I give different labels, but this is a problem about graphs. It's not a problem of labels. Okay? Path problem. And somebody painted every, modeling a road network. And somebody named every city in the graph New Jersey. New Jersey, New Jersey. Does that change the shortest path problem? No. The labels I have here are for a good reason. I'm adding these extra edges. What are my extra edges going to be? I'm going to connect each literal, okay, let's go back down here, in the flat structures, okay, to the correspondingly named vertices in the, triangles. So what am I going to do here? My problem here, you said my clause was V1, not V3, V4. So what do I have? V1 is connected to, we'll zoom it up a little bit, but you should know what's coming. V1 is getting connected to V1, not V2. 3 is connected. V4 is connected to, not V4 is connected to, not V4. So this is going to be my entire construction. I'm translating my SAT problem as follows. I'm going to construct my graph where there's going to be 2 vertices for every variable, 3 vertices for every clause. The variables are chunked together like that. The clauses are chunked together in triangles. And there's going to be an edge between any correspondingly named thing. So what happens if every variable clause contains V1? What are we going to do? We're going to connect V1 to every single clause. If there was a variable that was not in any clause, there would be no extra edges like there is here with this V3. Okay? Because V3 prime occurs, but V3 does not occur in either of these 2 clauses. Okay? That's my translation. Okay? What's interesting about it? Okay? First of all, any questions about the translation, the mechanics of it? Now, why did I do this translation? Note what happens. We showed that any vertex cover of this graph has to be at least this big. Correct? What if the original satisfiability problem, okay, was in fact satisfiable? My claim is the graph was constructed with this property in mind. This graph will have a vertex cover of size n plus 2c if and only if the original satisfiability problem was in fact satisfiable. Okay? It's clear that you could never do any better than 2n plus c. My claim is that in order to do 2n plus c, you have to have that original thing be satisfiable. Well, why is that? Think about what the difference is. Here's another fresh copy of it. Okay, here's my graph again. 2n plus 2c vertices will cover all the edges except those edges we added in the last spot. Correct? That last stage. How do we cover all of these other edges? If you think about it, if we pick all three vertices here, we cover all the edges coming to that clause, right? But we don't have a budget. If we're limited to finding a solution of size n plus 2c, we can't put three vertices in a triangle. Correct? Because you have just enough vertices to give two. You have just enough room in the cover to put two on each triangle. So what happens? The only way we could cover all three of these edges is what? If we took two vertices, and this edge got covered how? By taking this vertex in the cover. Correct? If we picked this edge, this vertex, and this vertex in our cover, my claim is we have covered all the edges associated with this clause. Right? Okay? Even though we only have two vertices down here. So what does that mean, if you think about it? We're really saying if we set V1 to be true, this clause is satisfied. Because this edge here, if V1 is true, this clause is going to be satisfied. Why? Because this clause contains V1 in it. Right? If we pick a variable, this thing to be true in our truth assignment, that will automatically make this clause satisfied. Once this clause is satisfied, we can set the other two, pick the other two vertices, okay, and that will take care of everything inside the triangle and everything else adjacent to this. Okay? Note that every single one of these triangle vertices is adjacent to the triangle, and there's one extra edge from VI in the triangle to the parent VI. Okay? If we pick that thing to be true in the cover, we're no longer obligated to cover this edge by picking that. Okay? And this is the idea behind the translation. Okay? Let me see. We'll show you in a second.
So this will also force us to choose the correct value for V1 or V1.
Right.
In the other clause.
Right, because think about what we're now doing. My claim is the following is true. Okay, let's look at the argument here, and then you'll see the beauty behind this construction. Because this is nice. This is nice. Okay? What I want to claim is if we do this translation, every satisfying truth assignment that you can find to the original SAT problem is going to give us a satisfying truth assignment for the vertex cover. It's going to give us a vertex cover of the right size. Why is that? Take a look at this one. My claim is for these clauses, this is a satisfying truth assignment. Correct? This thing has V1. This thing has not V4. Okay? The truth assignment V1 true, V2 false, V3 false, V4 false is a satisfying truth assignment to the clauses V1, V3 prime, V4 prime, V1 prime, V2, V4 prime. Does everybody agree that setting V1 true and V4 false satisfies this? Okay, it doesn't matter what we do with these other two variables. My claim is if you have a satisfying truth assignment, I can now figure out how to cover the rest of my graph using exactly two vertices per triangle. Why is that? V1 is true in here. So I know I don't have to cover this edge, do I? Not by picking one of the triangle vertices. It's already taken care of. So I will pick this one and this one to be in my cover. If this one here I know V4, not V4 is in there, if I pick this vertex and this vertex, I know that I have covered all the edges of my graph using exactly n plus 2c vertices. Why is that? Because of how I designed it. If there's a satisfying truth assignment, that means that when I pick these vertices, I have picked a vertex such that there will be at least one for every clause. There will be at least be one thing corresponding to what I picked, which is going to be covered. And then I have the freedom to use my other two to pick up that. My claim is any satisfying truth assignment implies a cover of that size. How many people believe? How many people do not believe? Okay? People seem stunned. Okay? Any questions about this? Question?
Yeah, I understand basically.
Sorry, okay, yes.
I understand basically what you're doing. The thing is, it's not intuitively obvious to me how you made your initial graph assignment here.
Okay. I mean, why did I decide to build my graph this way?
Yeah, like why did you, as an example, why did you choose not V1 over not V2?
Why did I choose not V1 over not V2? My claim is it doesn't matter which ones I chose.
I understand that. I'm just trying to figure out what you did choose.
Okay. Right. If you tell me that this is a valid solution to the SAT problem,
That's correct.
if there is, for any valid solution to the SAT problem you give me, any one, it's going to give me a cover of the right size.
Why did you choose not V1?
Wait. What do you mean? No, if you give me a SAT solution, if this is the SAT solution you give me, I'm going to pick the vertices corresponding to exactly what was in your SAT solution. V1 is true, V2 is true. Once I've picked that, I've got to cover all the rest of my edges. I've covered those. I now know that if this is satisfying, every triangle has at least one of these guys taken care of. You tell me which one you want taken care of. You can pick it, it doesn't matter. And I'll take the other two vertices in order to gobble up my triangle. Those three triangle edges, I need to pick two of them. Since I know this edge is already accounted for, by picking these two, I can account for those other two edges. If you gave me a SAT problem solution, there has to be a vertex cover of the right size. Okay? How many people believe? Okay? How many people do not believe? Okay, question.
Let's look at the second triangle.
Second triangle.
Okay, so you're covered by your initial example.
So,
Now your lower left choice there, right?
right?
Lower left. Okay, move your finger on it. Not the other edge, the one you chose. There, that one. So you're saying, essentially, when you add that edge, you could have arbitrarily...
What am I saying here? I'm saying here is my clause V1 prime, V2, V4 prime. I'm saying this is a satisfying truth assignment. That means that there's got to be something here that's true. Which is true? Well, if V4 is false, not V4 is true. If this is true, this edge is already accounted for. And so by grabbing these two, I gobble up that edge, and all the triangle edges. Everything's taken care of. If there is a satisfiability solution, this thing has to have a cover of the right size. How many people believe? Okay? How many people do not believe? Okay? So every satisfying truth assignment gives us the cover. What is the other thing we have to prove? That every vertex cover of the right size gives us a satisfying truth assignment. That's the sort of if and only if that shows that the mapping is right. So suppose I give you a vertex cover. Look, here's a vertex cover of the right size. Any vertex cover of the right size How many of these have to be in that vertex cover? Exactly one. Exactly one. Exactly one. Exactly one. How many of these have to be in here? Exactly two. Exactly two. If I take, since each one of these, the variable gadgets, exactly one of them is going to be true. Is going to be picked for my vertex cover. Let that determine the truth or falseness of my satisfiability thing. If you give me a vertex cover of this graph of size n plus 2c, I'm going to say, well, let's take a look. Did you pick this guy or this guy? You pick this guy, v1 equals true. You pick this guy or this guy, you pick that guy, v2 equals true. This guy or this guy, oh, v3 is false. This guy or this guy, oh, v4 is false. If you give me this thing, what do I know? If it is a cover, you've picked exactly one of these and exactly two of each of these. In order to have gotten those two of each of these, in order to have covered that third edge leaving this triangle, it had to correspond to one of the things that you picked. There was no way to take care of all three of these edges without having picked the right one of them to be true. Okay, one of them to be in our satisfying assignment. So we know that if you have a vertex cover of the right size, that means that one of these edges emanating from the triangle has to have been covered by something here, which means that if we make this truth assignment, it has to be a satisfying assignment, because we know that every clause has to contain at least one of these guys if you had a vertex cover of the right size. So what do I claim? Every vertex cover of size n plus 2c defines a satisfiability assignment. How many people believe? How many people do not believe? Okay? Has to be. Look through the argument. We've proven something about every single vertex cover. Contains n first stage vertices. The first stage vertices will define the truth assignment. We know that if that was a cover, we've taken care of one of these cross edges. So not only was it a truth assignment, but it was a satisfying truth assignment. Okay? Bottom line, every truth assignment gives a cover. Every cover gives a truth assignment. One problem is the same as the other problem. Vertex cover is neat, sweet, and NP-complete. Okay? Any questions? Okay, question.
The question is, what does it mean if you cannot find the satisfying truth assignment?
What does it mean if you can't find the satisfying truth assignment? Let's go back to this graph. You're telling me you can't do it. There's no way to satisfy a particular set of clauses. What does that mean? My claim is that means that there is no way to find a vertex cover in this graph whose size is n plus 2c. Because we know that if you were going to be covering this graph, so suppose let's say that there was no satisfying truth assignment. If there was a satisfying truth assignment, if there was a cover, then I could read off a truth assignment from that cover. Okay? And because of the way I constructed, if there was a truth assignment, a vertex cover of this size, that would have to give me a truth assignment that was satisfying. It clearly gives me a truth assignment because I know I had to have had at least exactly one of these. So that gives me a truth assignment. I know that if you have a truth assignment, it's got to take care of, if it's got a total number of vertices of this, one edge on each triangle has to have been taken care of by some mysterious means. Okay? The only way it could have been is if we claimed it up there. So if you have a vertex cover of size this, the thing had to have a satisfying truth assignment. And if you couldn't find such a thing, The only way you couldn't find such a thing would be if there wasn't a satisfying truth assignment. That's what we just proved. Okay? So if you cover the graph properly, you know that the thing can be done. Okay? If you can't cover the graph, it's not satisfiable. Okay? Satisfiability, we just translated the vertex cover. Neat, sweet, NP-complete. Any questions? Okay? Now let me warn you now, this is a very clever and beautiful construction. It's not the kind of construction you would be expected to come up with on your own. Okay? But it is important to see how we've translated a seemingly unrelated problem, satisfiability, into a graph problem. Okay? See why it works, admire the beauty, and realize that from now on, if you want to deal with graph problems, you don't need to work from SAT anymore. Now you've got a graph problem to start with. And that'll make the job easier from now on. Any questions? Okay? Think about it. See you guys on Thursday. Okay.